In this video, we're going to learn about the thermodynamics of mixing. Specifically, we're going to learn whether mixing of ideal liquids is going to be spontaneous or not. Alright, in the last few videos, we've been working really hard to derive expressions for the chemical potentials of various species, like gases or ideal solutions or solids in ideal dilute solutions and so forth. Time is now to try to find applications for those chemical potentials and see how that work that we have been doing pays off. What we do in this video is a simple application of those chemical potentials in which we simply consider two liquids that are pure. We're going to call them A and B, and we're going to mix them to form an ideal dilute solution, right? So we pour these two liquids into the same container to just generate a mixture of A and B, where A and B are interacting with each other, of course. Alright, and again the question is whether this mixing will be spontaneous or not. Alright, so because this process takes place isothermally and also at constant pressure, then we simply have to calculate the Gibbs energy of the mixing process, and if that sign is negative, then we will know that the mixing is spontaneous. If that sign is positive, it would mean that if you mix those two liquids, they would actually phase separate. That would be spontaneous, the separation, not the mixing of the liquids. Right, so we simply have to calculate the difference in Gibbs energy between the final point and the initial point. Alright, so for the initial point, this is going to be fairly straightforward. Notice that you just have that the total Gibbs energy will be the Gibbs energy of this plus the Gibbs energy of that. Alright, so that is going to be simply the number of moles of A times the molar Gibbs energy of A, but of course we call that the chemical potential, and then the number of moles of B that you have times the chemical potential of B. Now notice that here these liquids are pure, so those chemical potentials are simply going to be the chemical potentials of the liquids when pure. And that's what we use the asterisk to denote, okay, pure liquids. Now at the end, when they're mixed, the idea is that you're going to have now the same moles of A and B. This is not a reaction, right? So it would be maybe mixing toluene and benzene, or chloroform and some other liquid that does not react with chloroform. Right, so you have the same number of moles, and now you have a chemical potential, and the number of moles of B times the molar Gibbs energy of B. Okay, great. So again, to determine spontaneity, we simply have to do delta G, which is simply the final minus the initial Gibbs energy. But of course here we have the chemical potentials, and notice that these are not pure substances anymore. They're actually mixed. So the question is, well, what expression do we use for these chemical potentials? Well, so fortunately we have here our menu for chemical potentials under all of the cases that we're going to be working on. And in this case we're going to assume that these substances form an ideal solution. Okay, so if they form an ideal solution, where in this case, notice that the chemical potential is just going to be equal to the chemical potential when pure plus a correction from the fact that you're not pure. So that will be the same thing as Na mu A when pure plus RT natural log of x sub A, and then plus Nb chemical potential of B when pure plus RT natural log of the mole fraction of B. Alright, so that's how this develops. I'm omitting here this the specification that these are liquids, because obviously this is an ideal solution of liquids. Alright, so we subtract these from that, and what we see is that, of course, these chemical potential liquid terms, when pure, they're going to cancel each other out, and the only thing that remains is this Na, and then times RT natural log of x sub A plus N sub B RT natural log of x sub B. Okay, that is the what remains. That is the change in Gibbs energy. Okay, these are the new terms. So let's see if we can consolidate this a little bit and find out what the sign of this ought to be. We can remember here that the mole fractions are simply Na over the total number of moles, which I'm going to call simply N. And the same thing would happen for B, right? So notice that then the moles of each species are going to be the mole fraction multiplied by the total number of moles. Okay, and the same thing will happen here for B. Alright, so what I'm going to do then is simply replace that by just the total number of moles, mole fraction of A, and here this N sub B will be the total number of moles times the mole fraction of B. Okay, and this allows me to actually take common factor of nRT here, nRT, and then find the final expression here. So let's see if I can do this quickly. nRT, common factor of x sub A, natural log of x sub A, plus x sub B, natural log of x sub B. Okay, this is your final expression for the change in Gibbs energy upon mixing. So we can call these deltas of mix G. Okay, so I can write this like that. Deltas of mix G. Alright, so let's think about the sign here. Alright, number of moles is always positive, R is positive, the temperature is positive, all of these must be in SI units. And then we know that the mole fractions are also positive, right? But we know that the mole fractions are numbers between 0 and 1, right? So what that means is that this natural log is going to be a negative number, and that is also going to be a negative number. That means that the parenthesis is negative, and delta G is also negative under any conditions, right? As long as you're mixing A with B, then the mixing will be spontaneous. Okay, so yes, that happens when the solutions are ideal. And again, it's a nice corroboration that this chemical potential business that we've been handling actually makes correct thermodynamic sense. We expect that if you mix two liquids A and B, right, they're ideal. That means that the interactions with each other are of the same type, but the interactions among the pure liquids, then they should mix and they should not phase separate. Okay, great. All right, so there's one more thing that we can learn about the thermodynamics of mixing by taking a look at the origin of this spontaneity, right? So notice that the Gibbs energy always has, you can always interpret it as having two contributions, right? One that is enthalpic and the other one that is entropic. Right, so the question here is whether which one of these is causing the negative sign in delta G, or maybe a combination of them. Right, this term is really easy to interpret. Okay, so the idea here is that we have ideal solutions. And in those ideal solutions, the key is that the molecules of A interact with the molecules of B the same way that the molecules of A interact with the molecules of A when pure, and the molecules of B interact with the molecules of B when pure. And what that means is that when you mix these two liquids, there's actually no change to the overall forces felt by those individual molecules. And what that means is that this will neither be an exothermic or endothermic process. It will be thermoneutral. And what that means is that this is zero if they are ideal. That is the condition. Right, so what actually that means is that our deltas of mixing then has a very a nice expression, right? Delta mix of mixing, or yeah, the change in entropy mixing is simply the Gibbs energy of mixing divided over the temperature with a different sign, which is going to be this expression divided by minus T, which is going to be minus NR, and then x sub A, natural log of x sub A, plus x sub B, natural log of x sub B. Right? And this is always going to be positive because the parentheses will always be negative, but then you have a negative sign here indicating that this is positive. And that's exactly what you expect, right? The entropy isn't going to increase as you mix A with B. Okay, so we actually then learned that yes, mixing ideal solutions is spontaneous and it's entropically driven, right? So it's entropy. That is the gain in entropy that is driving this spontaneity when mixing two solutions. Alright, so in this video we have seen how to apply chemical potentials to understand the thermodynamics of mixing.